let's talk about the properties of exponential functions. So first of all, let's look at this equation for the first time. What do you see that's different? See, x is to the power. It's actually not lying on the floor like it used to be. That is part of the exponent, and that's what's make an exponential function. So how do we fill in the chart for the first and the last time? It's like this. So it's 2 to the power of whatever the x number says. So let's start with 0. 2 to the power 0 is equal to 1. 2 to the power 1 is equal to 2. 2 to the power 2 is equal to 4. 2 to the power 3 is equal to 8. And that's great. If you go into the negative numbers, well, 2 to the negative 1, that means it's 1 over 2, right? Because it makes it the reciprocal, 1 over 2. 2 to the 2 is 4, so the negative 2 is 1 over 4, and this would be 1 over 8. When we plot this, we would say, a little smaller so it fits. 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8. When I go on the other side, 2 to the negative 1 is 1 over 2, then it's 1 over 4, then 1 over 8, and then 1 over 16. And it gets closer and closer to 0. Very hard to draw, but we're going to try our best. Going to go something like this. And again, try to get close and close to 0, but try not to touch it. Very, very hard to do. What about 3 to the x? Well, 3 to the x, let's say I'll make that red. And 3 to the power 0 is equal to 1. Every number to the power 0 is equal to 1. 3 to the power of 1 is equal to 3. 3 to the power 2 is equal to 9. 3 to the power 3 is equal to 27. And when I go on the negative numbers, well, 3 to the power of negative 1 is 1 over 3. So the same numbers, but 1 over. 1 over 9, 1 over 27. That would be really hard to plot, isn't it? So if I graph it here, 3 to the power of 0 is 1. 3 to the power 0 is 1. 3 to the power of 1 is 3. 3 to the power 2 is 9. 3 to the power 3 is 27. That's not going to fit. It's going to go too high. And on the other side, it's going to be 1 over 3, which is less than this. 1 over 9, which is really close to the 1 over 27, which is even closer. Let's try to draw this. And something like that. And notice that, hey, the red line goes higher than the blue line on the positive side, but on the negative x, they flip around because, yeah, 1 over 2 is bigger than 1 over 3, right? So what happens with if I had half to the power of x? Well, half to the power of x would be something like, well, half to the power 0 is equal to 1. Half to the power 1 is 1 half. Half to the power 2, well, I just square the top, square the bottom. So it's 1 over 4. Half to the power 3, 1 to the power of 3 is 1. 2 to the power 3 is 8. Okay, there we go. And when I go negative, that's going to be the reciprocal of these numbers. That's going to be 2, 4, and 8. And we've seen these numbers before. It's the same as the blue column, except they're going in the opposite direction. And that makes sense because 1/2 is really 2 to the negative 1. This is like saying 2 to the negative 1 to the power of x. And that's just like negative x, right? Like saying 2 to the negative x, which means it's the same numbers, but going in the opposite direction. So when we sketch it, even if we didn't think about that, half to the 0 is equal to 1, half to the 1 is 1/2, then 1/4, then 1/8, then 1/16, and then it's reversed. So to the negative 1 would be 1/2, that'd be 2, and then that would be 4, and that would be 8, the next one is 16. And then we graph it, we draw it as best we can, and it would look something like this. All right, so let me just get decimals to do a better job for us so we can see it. And let's see all the points. This is half to the x, 3 to the x, and to the x. What do we notice? We notice that if it's 2 to the x and 3 to the x, it goes up. If it's half to the x, it goes down. Why would that be? Well, we'll talk about this in a second. But if the base is bigger than 1, you know that 100% is equal to 1 in decimal, right? So if the base is bigger than 1, it's more than 100%. If I multiply something that's more than 100% by itself, like 1.2, means I'm getting 20% more every time. If I'm getting 20% more every time, I'm going to go up. If the number is less than 1, like a half, it's 50%, that means I'm going to get half, I'm going to get half, I'm going to get half, I'm going to get less and less. But if it's 0.9, That means that I'm losing 10% every time. If I'm losing 10% every time, it's going to go down, it's going to go down, it's going to go down. Good. The other thing that really bothers me, this one, no, it's the first thing, but it really, really bothers me in my mind, is that this line, it keeps on going down and down for a very long time. Now, the example I use in class is like if I say, okay, if I am a certain distance from the wall, and then I jump every time half the distance, in how many jumps will I reach the wall? And I pretend that I jump a big jump, the first one, and then let's say I'm 100 centimeters from the wall. Then on the first jump, I'm going to be 50 centimeters from the wall. And then I'm going to be 25 centimeters from the wall. And now you're like, okay, you can reach it with your hand. Okay, but let's say I can only reach half the distance. So then that's going to be 12.5. And then it's going to be 6.25. And every time I go down, I get closer and closer. Yet I actually can't not reach it, no matter how many times I do it, if I follow the rule. Because just think about it. Once I'm going down to like 0.1 centimeter, which I'm basically there, but if I'm going to go half, that means I'm going to go 0.05. If I'm going to go half from that, I'm going to go 0.025. If I'm going to half for that, so let's go down to 1 micron. I want 1 micron, then I'm going to 0.5 of a micron, and then 0.2025 of a micron, etc., etc. Which means that this line, this blue line, is coming down and down forever and ever. Not for a long time, forever, to infinity. It never stops going down, yet it will never reach that line at the bottom of the x-axis. And that blows my mind. How can something be going down forever and ever and not reaching its destination? Crazy stuff. All right, so here are the main points. First one, all basic exponential functions, f at x equals b to the power of x, have the same y-intercept, and it's 1. This makes sense because f at 0 is b to the 0, and every number to the power of 0 is equal to 1. And that's why all the functions cross right there at 1. All the basic functions, which makes sense. Good. Second point. All the exponential functions are either always increasing or always decreasing to infinity and beyond. Remember how like quadratics, they go up and then it goes down, but for exponential functions, they're always going up or always going down. Here's the bothersome point. And exponential functions have an asymptote. This is a new word we need to know. A line that they approach but never get there. In the case of the basic exponential functions, the asymptote is y equals 0, which is the x-axis. All these 3 functions tend to try to reach the x-axis, but they don't quite make it. They don't quite make it. And point number 4, b to the x and 1 over b to the x have the same shape, but they're reflected over the y-axis. So it's a reflection. As you can see, the blue line and the green line have the same kind of shape, but they're being like flipped over the y-axis. They kind of make like a cup or a chalice in my eyes. All right, so those are the 4 points. And just to finish up, let's talk about this. I'm going to change this to b to the x because I'm going to use a different letter later on. So if my function is y is equal to b to the x, that's my basic function. Then what do I know? Well, if b is bigger than 1, the function is exponential growth. All right, it's going to go up and up. Why do we say that? Oh, it's because if the base is more than 100%, more than 1, I'm going to get more percentage every time, and it's going to get more and more stuff. So it goes up and up. When it's between 0 and 1, not 0, not 1, but in between 0 and 1, then the function is exponential decay. Decay, going down. Why is that? Because, again, if it's like 0.8, then that means I'm losing 20% every time. Lose 20%, lose 20%, lose 20%. I'm going to go down and down and down forever and ever. When the function is exactly 1, then I'm going to have 100%, which means I'm always going to have the same amount, and that's a horizontal line. That's not an exponential function. If the function was to be 0, that means I have nothing, so that's also a horizontal line on 0, and that's not an exponential function. But the one that's really interesting and not an exponential function is when the base is negative. So if I have something like y is equal to minus 2 b to the x, what would that look like? Well, minus 2 to the 0 is equal to 1. Minus 2 to the 1 is equal to minus 2. But minus 2 squared is equal to positive 4. and minus 2 to the power 3 is equal to negative 8. And now we get this like points that go up and down, up and down, up and down, switching on the x-axis, that you cannot actually join them because that doesn't make any sense. And they're not an exponential function. So the only ones that are an exponential functions are when b is greater than 1, and when b is greater than 1, or when b is between 0 and 1, but not equal to 0 or equal to 1. Those are the only 2 points that interest us. And just to finish up, change colors. The y-intercept is always 1. We already said that. And the x-intercept, there's none. It does not touch the x-axis because there is an asymptote. And the asymptote is y is equal to 0. That means it's the x-axis. Only for the basic functions. If I was talking, later on I'm going to give you transformations on these functions. And if I say 2 to the x plus 4, everything's raised up 4 units. So now the new asymptote is y equals 4. But for these basic ones, the one that look like y is equal to b to the x, just a number to the power of x, then our asymptote is always going to be y is equal to 0. All right.